Okay, what I want to do today, again, let's look at the syllabus, which you can go to. If you have the email, you can directly link. Otherwise, go to the stat web page, go to faculty, go to me, and then go down to 512. Just want to talk about a couple more things relating to this. So, did anyone have any questions about the main part of the syllabus? Do you have accounts? Everyone has accounts? You should email Steve Giesler if you do not. Did everyone try to get into RStudio? He should have given you instructions on changing your password. So you might want to change it from the default. In terms of the class schedule, I'll be updating this. Obviously, this couple days has been fairly busy, but I'll be updating it at least to some degree forward from here in terms of where we go. Today, what I want to do is I want to talk a little bit about more RStudio, including R Markdown, and basically some of the key things you'll need to know how to do. And then we'll look at just a few things that might be useful to you in terms of using R. So you can if you click on this, it will download Chapter 1 notes or Chapter 3 notes as a zip file, which you should be able to double-click to open. And then you can upload them to your account. If you look at RStudio, it has an upload button. Let me show you one other way that's a little bit easier. If you're sitting here on a Mac, you can go and say, connect the server. And then if you connect, well, let me tell you what to type in. Let me do that again. Go connect the server. And then typically you want to say AFP:// statw.edu. I think that's all you need. I don't think you need the 12,000 unless you're off campus. That's a :12,000. That works whether you're on campus or off campus. So if you have a Mac, if you're off campus, you can also get in this exact same way. There are other servers we have, like RC², and actually you can go directly into RStudio. So if I connect, but it really doesn't matter because you have your home directories and workspaces are linked across all our machines, so it's the same thing no matter how you go in. So then you have to log in with your password, and you can connect. And then I'll go into J Harner, which is my account. So at this point, you may not have anything here to speak of. So at that point, you could create directories, folders, and so forth. So I have a directory called courses, which has in it 512. And so, for example, here are the notes. So you could, if you download it, you can, if you've created a directory, or even if you haven't, you can just drag it directly. You can just drag directly from the desktop. You could drag a file directly in, just in a normal way. Or you can drag a whole folder in. So if you download it and unzip it, you can drag the whole folder in. Or you can actually drag the zip file in, and then you can double-click to unzip it. So any questions on that? So that might be a simpler way. That may be a simpler way to do it than sort of dragging files in one at a time directly into RStudio, or uploading them one at a time. Okay? So, again, I'll be filling this out over the next few days, so I'll send an email out about it. In terms of the lectures, I'll get those done as quickly as possible, but it takes about 45 minutes to post-process it to an MPEG from the format that it's saved in. And I have 2 classes back-to-back, so if I have meetings after this, it doesn't get done until the evening. But I'll try to get it done as quickly as possible so that ideally it's good to get it done here on campus, because each file is, like 800 megabytes. And so if I upload it from home, it's a little slower than if I do it here. So in other words, when you click on that file, it's probably somewhere around 800 megabytes or so. I thought about doing I'm kind of in the middle. I don't have the highest resolution, but I don't have the lowest resolution. So I could get a smaller file by doing it in a low-res format, but then I was a little concerned. I actually formatted it so it was optimized for an iPad, but, again, I could have gone higher, I could have gone lower. I say that because the iPad screen is small. It has high resolution, but it's a small screen, so. So there is a very high resolution format, but again, I didn't use it. But I think this will be okay. Now, this isn't the ideal way of doing it. It's good for you. What would maybe be better would be, and I have some software to do it, but again, it takes a while to do it. And that is, you can convert it, I can cast it. I can do a streaming type of, I can make it streaming as opposed to downloading, but that even takes more time. And the disadvantage there for you, of course, is that if you stream it, you must be connected to the internet, whereas if you download it, you can watch it even if you're not connected to the internet. So there are trade-offs. Are there any questions about the course, just general questions, before we go into RStudio? Okay. So let's go into RStudio. So RStudio.stat. So if you've logged in, you probably don't have to enter your password and all that again. I'm going to blow this up to full screen. And I'm going to get rid of this. I'm going to clear the console. What I wanted to do before I go any further is just notice, I just want to show you a few things, that if I'm going to create a new document, there are various ones you could create. The 3 that I'm most 3 or 4 I'm most likely to do is RScript is just a .r file. It just has R code in it. But it's a file, as opposed to interactively doing it on the console. And then RSweave is for doing reproducible research with embedded R code using LaTeX. And R Markdown, which is what we're going to focus on this course because it's easy, is where you have R code embedded in a Markdown document. You can also embed equations of several different types, but probably the most relevant here will be you can just embed the equation from LaTeX into the Markdown document. But again, the homework's going to be more a data set you analyze it, you talk about it, so there won't be much at all in terms of equations that you may have to write. So that's not really going to be much of an issue in terms of learning the syntax for equations. Now, you can also link to C or C++ files, and in fact, a lot of times what people do when they're writing code in R for a paper, let's say a research paper you're doing, is that you may have certain parts of that paper that are compute intensive, and R is not a fast language. It's an interpreted language. It's not fast per se. So there are numerous ways that you can speed it up. You can speed it up by doing parallel processing. But another way, and a common way, is that you actually program it in R, because you can do it very fast, and you say, okay, this part of my code is slow, and so therefore you either parallelize it or you say, okay, I'm gonna rewrite this part of the code in C, and then you can have what's called a foreign function interface to that code, and you can speed it up very fast. Now, in terms of this course and what we're doing, this is introductory statistics, so you're not going to get into the need of doing C or C++ in this course. But again, if you become more advanced in statistics and you start writing your own code to do things, because it's not done elsewhere, say you're a PhD student and you're doing original research and what you're doing doesn't exist anyplace. And so how are you going to do simulations? How are you going to, if you have a new theory, how are you going to implement the theory and test it on real data? Well, you're going to write code, and you're probably going to do it in R, because it's by far the best thing to do it in. And then if you're doing heavy-duty computing, you're probably going to write part of it in C or C++. You can also connect it to Java. So there's interfaces to Java also. This editor does not support Java at this time. And then there are other languages that you might argue that you should support, such as JavaScript or Python. So at any rate, mainly it would be R scripts, RSweaver, or R Markdown. You can actually, if you want to develop your own web page, you can actually, the nice thing is you can develop a web page and you can just do an HTML page using the syntax of HTML, which is relatively easy to learn. And then you want to embed R in HTML so that you can sort of impress people about your skills. Our documentation files are usually for packages. Okay. So that's what you can do. So and notice the menus, the edit menu is for editing, but the other thing you can do is, this is the console, you can clear it. And down at the bottom, maybe you want to just clear it. This is for coding. You can run regions of a code. You can what's called source a file, and I'll talk about that later. Then there's there are views which deal with what you show and what you don't show, like toolbars and so forth. Plots, which are managed down here. Sessions, we're in a session. You can terminate the session, or you in fact can terminate R if something happens. And that's the set working directory. I think I mentioned last time, that generally speaking, if you have a file in a certain directory, you want to set the working directory to that directory, because the file may create R objects, and those R objects you want them saved in the same directory as the code. So the code and the objects that are created in R should be in the same directory. By default, they're not, so you have to set the working directory to be the same as where the file is. Projects is a more advanced topic. If you're writing an R package, then you typically create a package, you create a project. And for those of you who don't know, and again, I'm just mentioning this in passing because a lot of you aren't going to nearly go this far, but a lot of people develop in this sort of community shared, what's called GitHub, which lets multiple people develop a project no matter where they are. And so you actually can tie a project to GitHub, okay, which deals with this version control. And so if you look at all software projects that are being developed, they're all, typically it's many people not maybe many, but more than one on a single project, and they have to be able to communicate. And I can't be editing a file while you're editing a file, and we have conflicts. So we have to have some locking mechanism. So if I'm editing it, you can't. But we also, if you did something I don't like, I want to be able to go back a version and get rid of it, let's say. So we have to have all those types of capabilities. Now, if you're creating a paper, let's say you're writing a scientific paper. First of all, I would argue that it should be reproducible. If you do it with Word and Jump, it is not. Reproducible means that let's say you write your whole thesis and you find an error in a few data points. Now, what would happen? And it changes everything. So, what would happen if you did it in Word? And you've got lots of embedded figures, and you've got certain text that came. You've got to go back and cut and paste or re-edit everything. On the other hand, in a reproducible way, all you do is change it. It updates everything that's a number, or it can if you write it properly. Any output that you put in, no matter how you format it, as well as any plots, they all get changed. Now, that doesn't mean that the conclusions might change. And if the conclusions change, obviously you have to, if you're talking about your interpretation, obviously you may have to go and modify that, but that's all you have to modify. Is that clear? So reproducible research is, reproducible research is, becoming more and more important, and increasingly I think journals are going to require it. That what you do must be reproducible. I should be able to take it and reproduce everything. So I should be able to check your assumptions. I should be able to check your model. Is it really a good model? Or let's say if I'm a reviewer for a journal, I should be able to do that. Yeah. Again, building is when you like building a package, and then we'll come back. There's a help files, and the tools do things like install packages. You actually you can install packages, but if you install them, they're only in your local workspace or your local directories, and therefore, if you do it, I won't have access. If I do it, you don't have access to it. What we try to do is we figure out, oh, we need package X. We can also globally install package X so that all of you have access to it. But you don't have permissions to do it. And I don't even have permissions from my account. There's an administrative account that you have to go in order to globally install packages. Now, on your own machine, you have a choice. Like on a Mac, you can save it in you can have multiple people with accounts, right? So if I go in and do it in my account and I store it in my own account, then I only have access to it. The other accounts don't. But on your own machine, if you're the administrator of that machine, you can install it globally so that every account on your machine has it. Let's say you and your spouse both have accounts on the same machine, then you may want it so that you both have access to those packages. So, by the way, you can pop up a Unix shell. So I could, if I say print working directory, this tells me, this says that I'm Mozart.sfw base, Harner. That is my home directory. I can ls, and that shows what's in that directory, and so forth. So you're actually doing a little Unix section right here without ever leaving RStudio. That's equivalent to doing something like this, where I go in and I could say ssh jharner at stat.wvu.edu, and then you have to go password, of course. And now if I say print working directory, or if I say ls, it's identically the same as that. So in other words, now you won't have to, you really don't need to do Unix commands. This is running on a Linux machine. This is Mac OS, which is also Unix. But here I SSH'd into the server. So this is actually the same machine. Although in this case, here I'm in RStudio, but again, your directories get cross-mounted every place. Actually, this isn't RStudio, it's just Mozart. So I can close that, and it disappears. So let me show you what happens if, let's do a simple Markdown file and see what we get. By default, it kind of gives you this little template here. So let's just take a look at this and see what it does. because what I want to do is let's see. Yeah. Okay, so I kind of got these side by side. Where did I go? I think I went to the help, Markdown quick reference. It brings up this over here, which is about all you need to know. That's why I say Markdown is quite simple. So if you want a really big title, you underscore it with equal signs. And then when you're typing text, you just type text. But if you want something in bold, you put asterisks on each side, double asterisk. Italics is a single asterisk. And here again is a bold. So if you look over here, you can see that the equal signs gives you a header 1. This is a header 2. 3 hashes a header 3, and 4 would be a header 4. So that determines four levels of headers. Again, this is the italic, is asterisk, whatever you say, and then you end up with asterisk, or you can do underscores. If I do double asterisk or double underscores, I get bold. So again, this is very easy to learn. If I do a list, and I wanted an unordered list, bulleted points, I could simply go item 1, item 2, item 3, and then I could indent it, and I can get sublists within those. Or I can have an ordered list, so I do 1, 2, 3. Or I could, then this would be, say, unordered within that. But again, it'll be in that order. So how do you end a line? You end a line with 2 or more spaces. You don't want an automatic word wrap. And let's suppose you want to put a link in your text so that you click on it, you go to a web page. The way you do it is you have some linked phrase which is going to show up that the user can click on, and you simply put the address, what's called the URL. You can put that address. Again, if you want to embed images, let's say you have an image, a ping image, and you want to do it. You put exclamation point. You put the alternate text. So in other words, the alternate text, there are browsers that don't show pictures. There are Unix browsers that you can use. And there's actually a reason that you might want to use that. If you were on a slow connection, for example, no pictures show up. You only get the text. And so you don't see all the ads. You don't download all the ads. All the flashing things. So the alternate text is what shows up instead of the picture if you have a text-based browser. Now, of course, you could have a subdirectory called figures, and then you have a ping in it. So this would let you, on your own machine, if you have a subdirectory that has the figure, you can do that. You don't have to go out to some other website to get a picture. If you want block quotes, you simply put the greater than sign, and it blocks it all. So how do you do R code? R code, you just put 3 backticks, and then you put in braces, you put R. You can actually name this block, and I'll talk about that later. And then you can actually just do your R code, and then you end it with 3 backticks. Now, suppose you want, if you're writing a reproducible research document, now you'd probably use LaTeX instead of this, but if you wanted to publish it to the web and have equations and so forth in R code, you may have a sentence and you want something in that sentence to be computed. Again, if it's reproducible research, every number should be computed from R. And therefore, even if it's in the middle of a sentence where I wanted to know the number of rows of the data set, so there were how many cars in the study? Well, this actually counts the number of rows of what's called the data frame cars and counts how many cars, because each row corresponds to a car. So that's a single backtick. R says this is an R expression. R goes and evaluates it. It pulls back the number of rows in the data frame, and it tells you. And so what you read is actually a number. tells you there are 25 cars or whatever. If you just want, suppose you want to publish code. You don't want it executed, you just want the code published, but you want it to stand off. Then you simply use 3 backticks to start it and end it, and then that it's like a monospaced font. I think it's indented. And so in other words, it's a block of code that sometimes you want to say, this is the code I use to do this, and you can put the code, and that's the way you should do it, so it stands off. And again, you can have inline code by simply having a single backtick. A single backtick. So it uses a different font. And when you're coding, you always use a monospaced font because things need to line up. You need to indent a certain distance and so forth. And so you always use mono fonts when you're doing this. Suppose you want something to be verbatim. A lot of times you just want it exactly as it appears. Again, you can use, I'm sorry, that's for code, which does show it verbatim. Okay, now LaTeX, you can have simply equations, and typically you just use dollar signs. But you could use backslash parens and left and right, and do what's called an inline equation. That's an equation that's in your text, so it's in the middle of a line. So you may have some sort of equation or algebraic expression. It's the middle of your text. You can use this. Display equations, and actually you put LaTeX in here. Display equations means they set it off separate as a separate paragraph. And so, again, you can use any of these styles. You can put horizontal rules and simple tables. Again, you can have links to say you have something at the bottom of the document. There's another way that you can link in, the various ways you can link in images. And then there's some special symbols and superscripts. Well, okay, here we have something simple over here. Now this mainly has R code. So how would we, well, first of all, if I wanted to, I simply could go in here and say run that line. I think this, why is that not working? Do I load a data set? Let me run this and see if it works. I thought that data set was available. I'm sorry, let me knit it. Oh, it wants me to save it. It wants me to save it. I'll just save it here for now and get rid of it. Let's see. Why is that not working? Yeah, it should work. Okay. Okay, so that's actually the output. Just notice that we have our title. We have, this was, we had a bold here, and we had bold here. Summary of cars, this gives a quick summary. And what this does is give the minimum, the maximum. It gives the median, the mean, the first and third quartiles, and so forth. For each of these two, there are two variables, speed and distribution. And then if I plot, the next thing I did is just a simple plot of cars, and there are only two variables in it, so it actually plotted speed versus distance. So you can see there's somewhat of a positive trend. Okay? So, again, I think that with a little bit of practice, I think that you can learn Markdown pretty quickly. It's a text file. But in this case, we don't end it with .txt, we end it with .rmd. Typically, the R should be capitalized so that Markdown knows, or RStudio knows. So again, this is a quick reference. Now, notice that if you want more, you can either go into the help file with RStudio docs, or a shortcut here is simply click on this. And so if this is using R Markdown, and this shows you side by side that, here you have a header 1, and then you have some text, and you have the italics and the bold. Here's a list. You can also create a list of dashes, and that's a bulleted list. And then inline code, I've got single back. This is actually monospace, but maybe you can't tell. This is a code block, and then back quotes. Notice that it's offset. So if you want something, you may have poetry and you want it to be offset, then you can use the greater than sign, and everything in that block gets offset. So if you want it to stand out, sort of an indentation. Now you might say, well, gee, this doesn't do nearly as much as, either LaTeX or Microsoft Word. That's true. But the idea is to be very simple. Now, having said that, this Markdown is developed. This one is a version that RStudio uses, the people at RStudio use. There are other more, like tables are pretty simple. In other words, the basic table structure supported here is fairly simple, but then there's something called multi-Markdown, which lets you do much more, including more sophisticated tables. But this isn't meant, if you want to publish your work on the web, this is a good way to do it. But on the other hand, if you send it to a journal, they're not going to take an HTML document, because what happens with, if you actually look at RStudio, if you go back and look under courses, you notice that that file test created, it started out with test.rmd. It created a Markdown document. So it had two steps. It goes from an RMD document, which embeds the code and the output from the code, and then that converts it to an MD document, .md, which is a Markdown document, and then that gets converted to an HTML. Now, I will mention there are ways that you can go from a Markdown document directly into a PDF slideshow. There are other tools available that can actually work on these files and create more sophisticated files. But at any rate, you probably do not want to edit this HTML file directly. So here's actually the HTML file, which was created as sort of the final step, but it kind of creates a lot of extra stuff, and there's a binary thing. Okay, so, and there's the graph. Okay, so I mean, there's certain things you could edit, of course. I mean, you could edit, there are certain assumed files. You know, HTML, there's CSS files that that it's using a default CSS file. And so there are certain default backgrounds and so forth. And so you could edit that, of course, but you probably won't. You'll edit the .rmd file and run it again if you want to change the file. You won't. It's unlikely you're going to be editing the HTML file. But it does create an HTML file, so this tells you in an HTML file you can embed programming languages like JavaScript. So JavaScript, particularly in a generation of graphics, and so let's say interactive graphics even, JavaScript is very commonly used. It might be called the language of the web. If R is the language of statistics, then JavaScript is probably the language of the web. It's widely used. It's not Java, despite the JavaScript name. But it's probably just about the most commonly used thing. If, for example, I do this, which is Apple's version of Windows 8, tiles in Windows 8. Which, thank goodness Apple doesn't jam down your throat, because I never use this. But that's the JavaScript skin on top of the, it's here if you want to use it. You can launch things, and it's called the Launchpad. You can launch from there. But again, that's JavaScript, and if I look at these dashboards, those are also JavaScript and so forth. So, but JavaScripts are used widely in graphics, and including interactive graphics. And so there are a lot of, Google has various graphics they have that you can use, and most of them are actually done in JavaScript. In fact, a lot of Google stuff that's facing you is in JavaScript. So, it's a good language to learn if you wanted to learn a language. By the way, the Markdown file, this is the Markdown file. Notice the Markdown file, which is created from the .rmd file creates the MD file, but the MD file is actually, by now it's run the R code, and it's actually, this is a Markdown file, and notice that the output is already in that file. Again, you don't want to edit that document, because if you rerun the .rmd file, it simply overwrites it. So you typically don't want to edit either the .md file or the .html file. You edit the .rmd file. Is that clear? If you do, you may be surprised if you edit the .md file, which you could. But if you do, then it could be overwritten if you run the .rmd file again. So that's just a warning. So you should spend a little bit of time, and I'm going to be doing examples. Right, and the first part of the course, for the next few weeks, I'm going to be illustrating .rmd files with what I show you in class, so you can sort of see that. Now, the files I have now are kind of they're kind of bare bones, but I'm going to add to them. So even though I've posted certain notes, I'm going to embellish those notes by this weekend, so that you'll have a few more comments and things, and I may put in some equations so you can see how to do that and so forth. So I'm going to talk about the binomial distribution some today, and so I'll probably be adding some. Here's the equation for the binomial. You can see how to do it. Again, equations will be something you don't really need to do hardly at all. Like if you're in biology and you're writing a paper, you don't necessarily put a lot of equations in, although you may have a prediction model or something. But again, it's pretty basic what you would put in, a scientific paper. You probably don't, even if you have a methods section, which you will, but it probably will not have a lot of equations in it. On the other hand, if it's a stat journal, that's a different story. So what I want to do now is I want to go into Stat 512 into notes, and let's look at chapter 1. And I'm going to, by the way, I had a file when I'm editing this book, and that file is actually a file that has LaTeX in it together with code, and I can actually take that file and just extract the code, and that's actually what this file is. Well, so what I did is I took this file and then I converted it to a Markdown file. And so here's the equivalent file in Markdown. So now what I want to do now is I want to set the working directory. And so I set the working directory to the exact same place this file is. So the working directory is now set to that file. So what I'm going to do is just take a look at this. Let's take a look at this Markdown file. So at this point, I simply have that underscore indicates a type of header, and these three also, I think, is a third level header. And then notice the 3 backticks here, and it says R. So that's a block of R code, or a chunk. And I've named that block, I've named it R norm, because I'm going to generate some data from the normal distribution. So So I could do this. You notice the run command. I could actually hit this. What you might do is this. I could say, let's knit this. It means let's create an HTML file. So I'm going to, if I click on this, it's simply, there it is. There are the results. Notice that, I'm going to get rid of that. Notice that it's just another tab. So I have a tab here and a tab. That's the code tab, and there's the output tab. Okay? So that ran the whole thing. But suppose you had an error. So you say, okay, I want to kind of step through each step one by one to see where the error is. So I'll show you how to do that. But what we did here is we generated a random sample, and I talked about this last time, so I'm now focusing a little bit more on the Markdown, but we generated a random sample of 100 from a normal distribution that has a mean of 10 and a standard deviation of 2. Notice that the mean is 10.18, and the standard deviation is 1.826. So you see they're close. Now, if I ran this code again, will I get the same answer or not? Nope. Well, actually, you will here because I set the seed. I said set.seed, and that means every time I run it, it's the same. If I comment out that statement, or if I remove that statement, then every time I run it, it's a different. But if you're writing a textbook, you probably don't want it to change each time. That way the student can reproduce it. And then in terms of R code, I'm doing a histogram. HIST is the R command for a histogram. So in R, everything is a function. So up above, you see a set seed and parentheses. Inside the parentheses are the arguments of the function. So the argument to set seed is 1, 2, 3. It's just a way of setting a seed. If I say 4, 5, 6, it sets another seed. Okay. And then now this is an assignment statement. I could also say y equals. So I'm using the older way of doing it, which in some ways I prefer it because you read the older way of doing it as y gets, meaning less than hyphen. Those two characters in a row means gets. If I say equal, it really means the same thing. It's assigned the value that's on the right. And what's on the right? Well, it's R code. I'm going to generate 100 numbers from a normal distribution. And if you don't give the mean and standard deviation, it will generate it. What do you think it generates it from? It generates it from a standard normal, which means a mean of 0 and a standard deviation of 1. Now, if you wanted to learn a little bit, about, about this, I could. Well, there are various ways I could do this. I could just put, I could put question mark, and I could put R norm. And if I do that, then it gives me this, and notice that I used R norm, which generates random numbers. It generates random numbers. The first argument is n. It tells you how many you want to generate, and then the mean and standard deviation. By default, by default, that says default is 0 for the mean and the standard deviation. If you don't give those arguments, use a 0 and 1. But I have 4 functions there: d norm, p norm, q norm, and R norm. I used R norm. What are the others? Well, the d norm is actually, you've seen the nice bell-shaped curve, right? What do you have to use to get the actual values of that curve? You have to use d norm. You may have also heard of the cumulative distribution function. What is the probability? If I have a normal distribution with a mean of 10 and a standard deviation of 2, and I say, well, what's the probability I'm less than or equal to 8? Now, what function would you use for that? You would use p norm. And then, so in other words, if I have, no, I don't want to do this. Let's see if this works. See if I'm still logged on. Oh, I'm not logged on. I get knocked out. I think maybe when I go to sleep, and unfortunately I need to set this so it doesn't go to sleep so much. see if I can get back on. So in principle, there's a program I have. Where did I put it? Called paper. So in principle, this ought to be interesting. In principle, if I have a normal curve, something like this, right? So I would use dnorm, I could actually plot that curve. So what does the cumulative distribution function would say compute this area less than or equal to that, and you do this for each point along the way, and you get a curve that goes like this from 0 to 1. It's not very good, it's actually more S-shaped. But at any rate, and if I look at this particular value x, there's a certain probability that's less than or equal to x, right? Okay. So if I put x down on this curve, then this corresponds to a certain probability, because this axis goes from 0 to 1, right? So this is called the quantile, and this is the probability, and this is the quantile. So I have functions that can compute that, which means I can given x, it can compute this value, or given this value, it can compute x. So what are those two functions? So if I want to compute, if I give it a quantile and I want to if I give it a quantile x and I want to compute the probability, I use p-norm, and that will be a number between 0 and 1. On the other hand, if I will give it the probability and want to compute the x value, I use q-norm. So x is called a quantile. So you're familiar with certain quantiles. For example, 0.25 is what? It's the first quartile. 0.5 is what? The median. The second quartile or the median, the 50th percentile, right? 50th percentile is a type of quantile. 0.75 is the third quartile. 0.6, it's the sixth decile, and so forth. All of those, all of those are quantiles. So if I wanted the 90th percentile, or the 0.9, if I wanted the 0.9 decile, or the 9th decile, then I could compute that by simply knowing 0.9, what x corresponds to that for the distribution I'm doing. So for example, going back here, if I wanted 0.9, it would be someplace up here, and it would come down, and that would get a value. So in other words, if you're given 0.9, I can get this x, which also corresponds to some value over here that has like 0.1 above it. So if this is 0.9, and this is, let's say, x2, and let's say this is x1 and x1. So if I wanted 0.1, if I want the value here that has 10% above it, which is the 90th percentile, right, then I could go at 0.9 and get the quantile. So you have all of those functions in R for a huge number of distributions. Discrete distributions, continuous distributions. The normal is a continuous distribution. The binomial we'll talk about is a discrete distribution. So but there's a long list of distributions. In reliability engineering, you have exponentials and y-balls and so forth. There's a large number of distributions. R has a very large collection. So at any rate, that's just some basic. You have all those functions, and this tells you the arguments for all of those. And also by default, for example, for these two, it's computing the lower tail, but you could also lower tail if it's false, it gives you the upper tail. So if you want to compute the 90th percentile, you would actually use the upper tail. So again, you should start exploring some of these functions. Now again, if I wanted to do these step by step, let's say I have an error in my code. I don't know where it is. Oh yeah, there is a basketball court over there, and there's a wall that they sometimes bounce up against. So suppose I do this. Okay, that I'm now doing these one line at a time. Now suppose I wanted to say, well, what are my values of y? I'm not printing them out here, but I could go over here, and once I've created y, I could say, okay, y whoops, I didn't mean there, I mean here. So I could say there are the 100 values of y. Now notice that R says that's the first observation, that's the 10th, that's the 11th. Notice that it labels, it's a vector of length 100, and you can sort of see what that is. So those are the actual values. I didn't print it out because they don't tell you a whole lot. But at this point, I could go in and interact with it if I wanted to just say hist. And if I just don't do anything special, it would just give me a standard histogram, which I then could look at. But we do a little bit more than the standard histogram below. So then I can continue on. So the point is that when you're writing code over here and you have a file and you have an error, you may want to go in and step through it step by step to sort of see what the results are, see what your problem will be. And now I'm going to go down to, I'm going to select both of these. So you don't have to actually. You see, this expression, this R expression, goes over 2 lines. Now, when I say run line, it only runs the line you're on. But it knows that that expression is not finished, so it prompts you for the next one. But I could just select it and run the whole thing. Okay. So if I look at this, probability equals true. It means I'm going to have instead of a frequency count, I'm going to have a probability axis. So it tells you the proportions in each category. And how do you define the categories? Well, I define breaks. I'm going to define, if I have a normal distribution that has a mean of 10 and a standard deviation of 2, then what is the probability, roughly speaking, that I'm within one plus or 1 standard deviations? Does anyone know that? It's about 2/3, right? Roughly. I mean, it's not quite, but it's. So that means between 8 and 10, I should get about, 8 and 12, I should get about 2/3. What about 2 standard deviations? Roughly what percentage are between? Yeah, about 95%. So, but now by the time I get plus and minus 3 standard deviations, it's a very high probability you're going to be within plus and minus 3. So what did I use? I went from 2 to 18. So my limits, in other words, I have breaks going from 2 to 18. My x limit on my plot, my x limits go from 1 to 19, and my y limit goes from 0 to 0.2. So why not 1? Well, I'm not doing a CDF. If I did a CDF, I'd have to go up to 1, right? But what I'm saying is I should be able to cut it off about 0.2 because I don't have a high enough probability of going beyond that. Maybe that was a little too conservative, I don't know. But at any rate, so I can execute this, and I'm going to, I want to define the breaks. I don't want the breaks to be at 1.8 and whatever. I want the breaks to be in multiples of standard deviations just because I do. So basically, I'm defining the breakpoints. And what do I mean by breakpoints? Well, let's execute this a minute. And this is sort of a review. So let's blow this up a little bit. So I forced it to have breakpoints at 2, 4, 6, 8, and so forth. Okay. Now, if I would have, I actually started out from 1, so there's a little gap here. I could have just done from 2 to 18 for the limits, but I put a little gap there. And again, you see that these are approaching 0.2, but none of them exceed 0.2. Okay. So this is a density axis. So in other words, what's happening here, if you add up these areas, what do they add up to? They add up to 1. So this defines a probability distribution. So based on my empirical sample, I could say I could compute the probabilities of this rectangle between 8 and 10. Now, if you actually computed the area of this rectangle, and then you compared it to the true probability between 8 and 10, it would be close, hopefully. Okay? So again, if I didn't set the seed and I did this time and time and time again, on average, these rectangles would, if I did it a bunch of times and averaged them, it would be exceedingly close to the true value between 8 and 10. And as I go to infinity, the number of times I do it, it would converge to the true probability. Any questions on this? Now, if instead of doing this, I would have just have clicked on the first line, notice that it did this, but if I click on it again, it finishes it. So it didn't do anything when I just clicked on the first line, but it knew the expression, because I have this parentheses here has to be closed by that parentheses. So the arguments have to be closed. Why do I have two parentheses? Well, because I have another argument. I have this C. This C is a function, and it has parentheses also. So I'm defining quite a few functions. Sequence is a function. This says go from 2 to 18 by 2, 2, 4, 6, 8. Okay. The x limit, the x lim and the y lim tell you the lower limit and the upper limit, and this tells you the lower and upper. So it tells you how big to scale the x-axis and the y-axis. Okay, and then then I'm actually defining x values that I'm going to use in a function called curve. Now, does anyone see something interesting about the function curve? There's something very powerful there. See what it is? What's the first argument to curve? It's a function. I have a function embedded in another function as an argument. You can do that in R. It's a very powerful feature. I can embed functions within functions. So the first argument, it says I'm going to create a curve where I want the densities. Now up here I was using R norm. Here I'm using D norm because I need the density. If I'm going to draw this curve, I need the values of the curve. If I'm drawing this curve, I need the values of the curve, and D norm will give you that. So my first argument is giving me the D norm for x, where x is going from 2 to 18 with a mean of 10 and standard deviation of 2. Now, if I would not, up here, if I wouldn't have said probability equals true, and I would have done a frequency histogram, then this wouldn't have been good. You would have had this very different histogram, and you'd have a density which might sort of fit it, but it wouldn't fit it in the sense that it goes through the tops of the bars, because the scale would be different. See, here I'm assuming that I have a density function. So by saying probability equals true, it puts the D norm and it puts this histogram with a D norm probability of true on the same scale as using D norm, because it's computing probabilities. So if I run that, let me scale it. Let me blow it up. And you can see that the fit is reasonably good. Now, if you would have done 1,000, instead of doing 100, it would be better. And then you might want to make this granulation. Right now, I have, I'm going from 2, 4, 6, 8. You might want to have a much finer. You might want to have a lot more bars than just, what do I have, 6 or 7, 6 or 7. Depending on what your counting knows, it's I guess 8. So at any rate, if I had a lot more observations, you don't want to have too many bars if you don't have a lot of observations, because you don't want zeros and you don't want it to be jumping around. So you've got to sort of fit the number of bars reasonably well to how many observations you have. Now, if you do a histogram, if you just do a histogram on data, I did it on generated data. If you do it on data, again, by default, if you don't specify the breaks, R has a default rules, and they have various default rules. So if you actually go in and say, look at hist. So if you look at hist, you should use the help quite a bit. This tells you about, what it does is it tells you all the possible arguments, and then it tells you what they mean. So in terms of breaks, it tells you what kind of breaks you could have. And you can see there's a huge number of possibilities. You can have probability plots, frequency plots, and so forth. So if you look at this, you'll see there are a lot of, and then they tell you, they sort of describe, this. And if you notice, it says the default for breaks is Sturgis. And so this actually has a class, and you have other algorithms that you could use. For example, David Scott, there's an algorithm for him, and so forth. So there are a number of different rules for determining how many categories you have in a histogram. The default is Sturgis. It's pretty good, but you could try alternative rules if you want to. And the values you get, you actually create a histogram object. Usually we just display as a graph, but there's actually built-in stuff, and so you actually can examine that object to see what the breaks are and the counts and so forth. I didn't save the histogram as an object. I said, okay, I could have saved it as an object. So when I said hist as a function, I could have saved that in an object. Then I could have plotted that object, but I could also examine that object. So R is extremely flexible in that way. So any questions on this little example? This is sort of a chapter 1 example. Okay. What time is it getting? Yes.
So if you had set the histogram to an object, how would you have printed it off? Just by typing the object name?
Yeah, I think typically there's a default print, and I think if I so if I do that, actually it's all of this. Okay, why is it not found? Oh, I misspelled it. What this is telling you is it tells you what the breaks are, what the counts are. This tells you the counts in each break. Tells you the density at each of these breakpoints. Tells you the midpoints. So these are the objects. These are the objects. These are what we call attributes of that object. So there are reasons why you may want to save that if you wanted to, because you can actually extract all that information and use it if you want to. So a histogram isn't everything in R is an object. And this is actually what's called a list. This object, it has attributes, and these are the attributes of the object that I created. Okay. So by default, an object has a print method. By default, it's printing the attributes of the object. So, okay. Okay, let me just quickly show you. So time is going fairly quickly here. Let me show you, let's go up to chapter 3, which is the binomial distribution. I just want to show you a few things, and I guess we're going to have to talk about it next time. So I'm going to look at this file, and I'll set the working directory as this. And so what I'm doing here is the binomial distribution. And so just to show you, if you have the book will not have all this is the code that you can think about inserting in the book to create certain things, but the book doesn't have this code that you buy. So I could, for example, if I go into here, Okay, so if I want to go to chapter 3 on the binomial distribution, basically you should actually review the first part of the book. But in particular, the binomial distribution is something you should know. And so that's chapter 3. Chapter 2 is a review of basic probability. So if you're kind of, things like mutually exclusive, the addition rule, the multiplication rule, all that kind of stuff, if you're a little shaky on that, you might go back and look at chapter 2. Chapter 4 is on the Poisson distribution, and that's probably not something we're going to be pursuing much later on, but the binomial distribution is fairly important, so you might want to, you should probably take a look at it. Basically, if you're computing binomial probabilities by hand, so what would be an example? An example would be you toss a coin 10 times and how many heads you get. Well, it gives 0 to 10, right? So how do you compute that? Well, the probability of success on each one is 0.5. You assume you have independent events. You assume that the second toss is not influenced by the first, and so forth. And so it's fairly easy using the addition rule and the multiplication rule to compute these probabilities by hand. Fortunately, R does this for you. Again, it can be, there's a binom function, binom, and there's a D, there's for density to compute the probabilities of the binomial. You compute the quantiles. You can compute R for generating random values from a binomial, and so forth. And so you have those same 4 functions that with the binomial. So let me just indicate that, let's suppose, just as an example, suppose you're talking about blood type, and there are 4 blood types, but let's suppose you're going to say, is it O or not O? Well, if the probability of an O blood type is about 0.4, then the probability of not O is 0.6, right? By the complement. And so, you say, okay, if I choose 4 people at random, what's the probability that none have type O, that 1 have type O? You could actually compute this by hand, right? Because it's not so hard as long as n equals 4. So the possible outcomes, if none are, so you have n, if you select 4 at random, then you have n. But if you want to say what's the probability exactly 1, then it could be the first, the second, the third, or fourth. So this would be computed as 0.6 times 0.6 times 0.6 times 0.6. This is what? 0.4 times 0.6 times 0.6. Because I'm using the multiplication rule for independent events. Each one of these, in fact, each of these is 0.4 times 0.63 times, so it's 0.4 times 0.6 cubed. And I add them, they're all the same, so it's 4 times that. Or put another way, it's 4 things taken one at a time, which is 4. Now, how many ways can I get exactly 2 that have type O? Well, that's 4 things taken 2 at a time, right? So there are 6. 4 factorial over 2 factorial times 2 factorial. So there are 6 of those, and this is 3. And so I can use the basic rules of probability to compute these, using those particular rules. And the book goes into a lot of detail, but I could also compute them, and I'll do this next time, but I can also use d-binomial. And so this says I'm doing an argument 0 to 4. The second argument is n equals 4. And the third argument is p equals 0.4. So this is actually computing the probabilities using R, using a d-binom of, and I actually named these so you can read it, 0, 1, 2, 3, and 4. Those are the probabilities computed by R. Okay. And there's a plot. To plot it, I can just compute 0 to 4. I compute y, which I just computed. And the type equals h means h is a type of plot that says plot vertical lines at those points. And so that, and I labeled the x label is y and the y label is p of y. So that was pretty easy to construct and compute. By the way, that's how you do it in SAS. So at any rate, this goes through some detail, but in the bottom line is, someplace down here, is the formula for the binomial if I have n trials and I want to know what's the probability of y successes where y is 0, 1 up to n, then it's n things taken y at a time, p to the y, which p is the probability of success, 1 minus p is the probability of failure, 1 minus p to the n minus y. That's the formula. Okay. So I'm probably going to stop here pretty soon. I should mention that the expected value of y is a random binomial random variable, is n times p.
Yeah, this model is easy because you know the exact number of p, like 0.4 in your case. But what if you don't know the number of p?
Well, then you have to estimate it, and the maximum likelihood estimate is simply y over n, where y is the number of successes. Okay. And in fact, the book later on, if you talk about, there's an example on testing hypotheses using a binomial where you compute the exact significance level, which is probably not over 4 because it's 0.05 because it's a discrete distribution, and the p-value. I'll talk about that next time. But you can also go in and if you want to estimate, then p hat is y over n, and it's what's called a maximum likelihood estimate. And in fact, this graph shows, this is a graph of 3 different values of p, and this tall bar here is y, and that's, if you multiply n times p hat, that would actually be y. So that tall point is the maximum likelihood estimate. And I think this is 0.3, p equals 0.3, 0.5, and 0.7, I think. So hard to read. So yeah, and so if you get an estimation, the question is how do you put a confidence interval in? Well, the confidence interval is not, if you have an exact confidence interval, it's not quite as easy as if you have a normal distribution because you have a discrete. But I'm going to spend a little bit of time next time going over this code and going over this, because you should know, if there's anything that you should review, you should definitely know the binomial. But if you know the binomial, it implies you also know something about computing basic probabilities. Another thing that you need to review is the normal curve, which is a continuous curve. And so again, chapter 2 talks about discrete and continuous random variables. So you should start reviewing those early chapters. I'm not going to spend a lot of time on it. I'm going to be jumping to chapter 8 fairly quickly, which gets into statistics. Chapter 8 I still consider review, so I'm going to go a little fast there too. Again, you should know this from the prereq. But I'm realistic. You may not all know it. So you may need to go back and review this basic material. So you can look at the first part of the book. Any questions? Okay.